Hey, Al. People are still trickling in. I'll wait for Deanna to join as well, since I think she has the. Oh, she just joined. Has the main topic to talk about.
Yes, hello. Um, I've been working on how we can have a better firmware transparency story uh, in Compute Engine for confidential computing. Um, and while we work on, building all of the technology to get our transparent build outside of our internal infrastructure walls, um, it seems like Red Hat's approach of allowing the guest VM to bring their own firmware is going to help some customers fulfill their needs even better than when we have our transparent offering, just because they will have more purpose built functionality that will serve them better. Um, and I do like this idea. I think that the interface that is being proposed uh, with the firmware config interface kind of bifurcates this space of how to instruct virtual machine monitors on how to load these confidential VM initial states. And I think Microsoft has been uh, trying to push a format uh, to support um, more general firmware loading for confidential VMs called IGVM that is probably going to be um, something that we can more readily govern across virtual machine monitor implementers than the communication mechanism um, of that file to the VMM. So I wanted to just bring the different VMM implementers together and the proposers of the FUKI approach to discuss this a bit more, because I saw that there were some concerns about the reset behavior that IGVM does not um, yet have a way to express. And we have John Lang here, who understands the format, and Chris Wu, who understands the format. So this is good. Wanted to open the floor to folks who've had thoughts about this as well.
So, Diana, if I could ask, who do we have from the FWUKI side?
Ani Sinha here,
Okay, good.
and
I just
and George.
thank you.
Gerd is also here.
So perhaps while people are collecting their thoughts, I could ask a little bit more information about the um, the memory behavior of the reset, where the shared memory is expected to be kept alive through the the reset. I'm a little unsure what the purpose of that is. Can you speak to that, Ani?
Right. So this was before we were thinking about IGVM. And we were proposing, so this, a little bit of background context on this. So Alex Graf from AWS, he was the one who actually originally came up with this idea of Fuki. He is not in this call. I have to forward the meeting invite to him as well. So a lot of those initial thoughts were around how AWS implements their hypervisor and their basically the limitations that they have on their side to do this kind of a implement this kind of a thing. So the idea was this, that initially when VM is started in the cloud, that VM obviously comes up with the firmware that's provided by the cloud vendor. But then after like say a reboot, a reset, we need to activate this firmware that the end users provide through this mechanism. Now there has to be a way to kind of transfer data between this first state, which is quote unquote insecure, to the second state, which is quote unquote our trusted and secure state. So the idea was to use the memory to basically pass this data around. Now, memory is obviously two types. One is the shared memory, the memory that's shared with the hypervisor and the host, and the memory that's private to the guest. Now, I believe both the kinds of memory is, so the way that the QEMU implements today VM resets is that normal VM resets. I'm not talking about Fuki resets. Fuki resets is a different story. Normal VM resets does not change the memory content. So all memory remains as is through the reset process. So the idea was to basically leverage that and pass data between the first stage and the second stage, and then somehow make sure that the second stage also knows what components the first stage loaded and where. So basically where the firmware is, where the kernel image is, where the kernel command line is, etc. So that was the part that for which this firmware config interface was used to basically do this handshake between the first stage and the second stage. But now that we're talking about IGVM, and to be honest, I have gone through the discussions, but I haven't had a lot of time to put some thoughts on this with how IGVM would work. Maybe Gerd has more ideas because he's been putting a lot of thoughts on that. With IGVM, some of these is going to change, but I believe we still need to pass information between the first stage and the second stage through firmware config, and that's the part where I believe we're discussing on the mailing list, like what information needs to be passed and what the hypervisor interface would look like with the IGVM in the picture right now. And most of the complications are now going to be handled by IGVM, not by the hypervisor. So hypervisor does a very simple, basic things, and then mailing list. This is QEMU Devil mailing list. I can point to the thread as well. But yeah, so that's where all of these things is coming together. And we had a discussions on this internally, and basically the current proposal is to go all in with IGVM. So basically only support IGVM, and not the initial thing that we were proposing, that like basically the guest uses this interface to just pass the firmware image from the first stage to the second stage. So don't use that. Just use IGVM, because IGVM can handle pretty much everything that we can think of, and hopefully that should solve most use cases, most common use cases. So that's where we are right now. I need to check this. Yeah, I think so. V6 is the one that generated all the discussions. Yes, this is the one, I believe.
I think John has his hand up, so I'll give him a chance to talk here. I'll interrupt for a second.
Thank you. I apologize. I'm coming into this conversation without much context. I'm hearing some things that raise more questions for me than answer anything, largely having to do with the security model and the confidentiality boundaries of whatever we're talking about. So we're talking about, well, let me ask first. I've heard the term reset and I've heard the term firmware replacement. And the first question I'm trying to grapple with is the idea that you run and boot an operating system and it runs into a fully functional state and then it decides to reboot into a new image? Or are we saying there's a first stage loader whose job it is to kind of, establish the environment, figure out what firmware it really wants to boot, and then boot into the actual firmware?
And that's yeah, the second.
So the second one is what we're talking about.
Yes, exactly. So basically, the first stage boots, it realizes that it's not running the firmware that it expects. So it sets up the environment and then triggers a reboot. And then the second reboot does all the magic. So the second reboot is where the IGVM does its thing, sets up the memory and firmware, loads it. Oh, Alex Graf is already here in this call, so great.
So we're talking about confidential VMs. What attestation and measurement behavior is expected here? Are we assuming that the first to second stage boot happens within the life cycle of a single VM and its initial measurements and attestation report? Or are we assuming we boot something, it prepares a second environment which goes all the way back to recreating the confidential VM and reinitializing the measurement state, so that by the time it is fully running, it is as if the first stage had never run?
You are correct. What you just described is correct, yes.
Okay.
So the first stage is just to detect that it is not running the state that it expects. So the second stage recreates the entire confidential context from scratch, and then whatever you just said, that's all that happens.
So from the relying party point of view, the first stage doesn't matter. It's just a convenience for the cloud provider to decide what it takes to get the correct image running. There's no reason that any breadcrumbs from the first image have to be attested at all. Correct?
Correct, yes.
Okay.
They shouldn't.
Thank you for helping me understand this now.
Right. So you're booting an untrusted environment. The untrusted environment then gets the chance to rip out the whole VM context, create a new one based on its own description, and then recreate a complete second environment.
Right. Start over again.
Start completely over again. Correct. However, we need to differentiate between two different concepts. There is a virtual machine as seen by the hypervisor, and then there's the virtual machine as in what hardware actually considers to be a VM context. And here we're basically saying the virtual machine that the hypervisor has as a construct stays intact, but the hardware construct gets recreated.
This behavior that you're describing sounds like it is a feature that is very specific to QEMU.
No.
No, you think that this is a feature that will be demanded by VM owners in all clouds?
Well, I'm interested in it.
Okay.
I'm interested in it.
Okay.
And other operating system distributions are interested in vending their own firmware so that they could use this interface.
So
Yeah, I
think
think
of
for-
it.
But is there an assumption that the firmware that they choose to bundle is a derivative of OVMF and that the VMM
No.
supports the contracts that OVMF
Yes. Okay.
expects to use?
Wait. Yes and no. So the firmware is obviously target specific. So if you have a Fuki that happens to that you're loading, you would run that in AWS, for example, then it would have to load a different OVMF binary most likely than if you were running that in GCP, right? So it is using different backend. It needs to use different backend binaries. However, there's actually one more thing all of this unlocks, which is the really cool part of it. So at first it totally gives the image owner full ownership of every single line of code that runs inside a VM, which is key, right? Because that's the only way you can actually tie the whole security link back from customer all the way to AMD or Intel for that matter, same difference. The really cool thing this enables is that your payload doesn't have to be OVMF. Your payload could be an SVSM. So if you really want to go and also provide a VTPM, you can now allow your customer to provide their own VTPM implementation, which also means that if there is a 0-day in that implementation, it's not your cloud provider who you're trying to remove from the trust boundary, right? That gets to know about it and fixes it. It's your customer or your customer supplier that goes and provides them with a VTPM.
Yeah, so the scenario you're describing, it sounds interesting and compelling, and the thing that I'm struggling with at a machinery level is why there is an assumption that you must boot a shell VM, which then takes responsibility for loading the customer's desired image, rather than just booting directly into the customer's desired image to begin with. And that's why I was wondering if this two-stage problem really is specific to QEMU or, you know, a subset of the VMM implementations. Because I can also imagine that a VMM implementation might say, I don't need 2 stages, I just point at the customer's image and go.
Correct, which already exists today. So you have that today. That's completely present. You have multiple implementations like Cloud Hypervisor can do that, QEMU can do that. All of them can point to a specific customer kernel, initRD, command line.
I see.
And then go and boot that and validate it.
The desire then is to say customers want to have a standard that they use to bring a format to the cloud.
Correct.
So that they can take the same image and run it in any cloud.
Take the same image to run it on any cloud, but also don't have to worry about multiple artifacts. One thing that happened in the cloud in the last decade, right? We moved away from things like ARKeys and ARIs, like distangled. Like we used to have completely separate kernel images from initRD images from disk images, and all of them went like they converged into the VM template is only a disk image, and that contains everything you need in order to run this disk image. And to bring that same semantic into your confidential VMs, you want to be able to have some bootstrapping mechanism from a disk image.
Sure. Although I think you already stated that you're not truly going to get to a single uniform artifact across all clouds because the OVMF implementation you use in AWS will be different from the one you use in GCP.
That's
Azure doesn't use
implementation
OVMF at all.
You can hide that. You can hide that. So you can have a single Fuki that, for example, goes and includes multiple OVMF images, and based on DMI just decides I'm choosing this one to boot. So say if you're a customer, and when I say customer, I mean an end customer that has no idea what any of this is doing, right? They go and buy a distribution from Red Hat or from SUSE or from whoever and want to basically have that contract that says, I trust Red Hat, I trust SUSE, I don't trust GCP. And then they want to be able to say confidently that they just go and launch the Red Hat army or the SUSE army or whatever, like the OSV army. And that one is safe to consume because then they can tie their attestation back to something that their operating system vendor actually provides.
But that disk image doesn't include OVMF. That disk image is just the distro.
No, it does.
Oh, it includes both of the OVMFs, both of the clouds?
Yes.
And does it include the firmware image that would be used in Azure? or is it
Yes.
only for,
Yeah.
okay.
If Azure implements the same mechanism, right? I mean, all of this is not implemented in any cloud today. But yes.
Oh, I see. So you're talking about everything you're doing is conjecture.
Is what?
Everything you're saying is conjecture for unification.
Yeah.
Okay.
And pushing the boundary somewhere else. So today what you have is you effectively every cloud provides their own firmware. And then customers rightfully ask, like, why should I trust your firmware blob? Like I didn't build this, and you could have injected some random code in there that I don't want to trust. Right? We try to mitigate some of that by making the code public and reproducible. And that has been very big trust-wise with customers so far. But I don't think it goes far enough. Right? We want to go one step further and just say, look, you don't have to trust us at all. Trust your OSV, because you have to trust your OSV anyways with whatever code you're running, because if you put a backdoor in the kernel, then you're toast, right?
So I think what you're trying to standardize is a lot more than just a packaging format, but you're trying to standardize a bunch of I guess, manifestation challenges where you need to be able to figure out how you pack an SVSM and or multiple firmware images in there. And you have some sort of runtime that can decide, based on which cloud this thing is actually launching in, which image you're supposed to make resident.
There is already a mechanism in UKI to do that, to detect. Basically,
But
it calculates
UKI is
server
not
IDs and
UKI is not standardized across VMM implementation. So you haven't hit your universal truth yet.
Perhaps it might be useful to describe the mechanism you envisage using to distinguish between the different clouds for firmware boot.
Arne, you have that implemented already.
I had a lot of things implemented, but which one are you talking about?
The DMI matching.
Oh, yeah, I have that. Yes, already. That's in the UKI, yeah.
So speaking on behalf of Hyper-V and Azure, I don't know what a DMI is, and I'm pretty sure it doesn't work in our cloud. So is there some effort that
I am 99.999% sure that you absolutely do support DMI.
Yeah.
Everyone does. Like
Right. But we're
Okay.
using different terminology, so could you just define it so we know what we're talking about?
Let's go and do that. So what is the matching mechanism? So every machine since 2000 basically provides tables, multiple different tables that are just descriptions in hardware of in RAM, descriptions in RAM of what hardware looks like, and there were different generations of these, yada yada. One of them is the SM BIOS table, also called DMI tables, which contain a machine readable representation of things like, this is my motherboard name, this is my chassis name, this is my DIMM configuration, and I have like 5 DIMMs, no, wait, not 5, 4 DIMMs of so and so many megabytes each, and so on and so forth. Pretty much every operating system expects that to be available and present. So everybody exposes them. And this is even pre-ACPI, right? Like this is bread and butter. These tables in the cloud also tell you which cloud you're in and which specific target platform of the cloud you are in. So you can look at that table on boot and determine, oh, I'm in this environment. Let me go and boot into this particular target firmware. But obviously you are creating a stable ABI between firmware and hypervisor at that point. That's the downside. I agree.
So if I understand it,
So-
this DMI table has really been a fuzzy string. So this match must be slightly fuzzy as well.
Well, and we don't use that in any of our confidential VM configuration boot processes. We may generate that on behalf within the confidential environment on behalf of the operating system that runs, but we don't have one of those to make a decision in the the first stage of the confidential execution to decide what host we're on.
I don't follow. So if you launch a
Yeah.
confidential VM today and you run DMI decode, what do you see?
Well, the DMI tables are generated in the confidential environment.
That's okay. What does the customer in the VM see when they call DMI decode? Would they be able to
But hold
say,
on.
I
But
am
here,
running
Wait. I
in
think
Azure?
I think we're missing the fact of where you do the match. I think John is assuming you're doing it right at boot, which is impossible in Azure. But I believe you're actually doing the match as part of the process from going from the first to the second image. Is that correct?
That's
Correct.
correct. Yeah.
Okay.
oh, I see. I see.
You do a full boot, where full boot is an implementation detail here, right? So you were asking earlier whether we're doing this super early or late. None of this matters to the hypervisor. From the hypervisor's point of view, it boots a fully working functional virtual machine. And then the virtual machine decides at some point of its boot, which could be at the UEFI stage, which could be way later in some KExec mechanism. No one cares from the hypervisor point of view. Could decide sometime later, let me go and perform that specific target specific reset to go into my other firmware. And at that point, you do
But
have DMI available.
right, I guess I am assuming then when you get into the second stage, the version of the second stage that is capable of running in Azure versus the version of the second stage that is capable of running in AWS or wherever will have different co-RIMs associated with them because they have different contents and different measurements. It is the
Correct.
untrusted world that is making a decision about what to load into the confidential world. And it
Correct.
will load different contents.
Correct. And then it's
Doesn't
so
that mean you have different
Mhm.
different artifacts so that it can decide which one to load? Are you assuming that you have one file that has 3 or more co-RIMs in it
correct.
with directives? I see.
Correct.
UKIs can package multiple firmware or IGVM binary files depending on, and then the matching can be based on this Alex just described.
Okay.
So-
UKI sounds to me like a QEMU specific concept
No,
because
no, UKI is a systemd thing.
oh,
UKI
okay, fine. But it's not doesn't exist in Azure or Hyper-V.
It does exist in Azure because you
Or
are
is-
using Linux distributions as virtual machines, which then have
Oh,
which then are using
doesn't
UKIs.
care whether it's Linux or Windows. It's just operating system agnostic, as long as
Right.
you're
So
running
again,
file.
I'm not up on what UKI is. I was assuming this was some sort of contract between the guest and the host.
No, UKI
No.
is basically a PE binary that contains multiple sections of different binaries just for signing purposes.
Oh,
It's just a container wrapper format for it's like, think of it like a single PE binary bootloader. You create one PE binary, one UKI PE binary that now includes a bunch of sections with subcomponents. Usually you would include a Linux kernel, a Linux init MFS, and a kernel command line as part of a UKI build. And then you have a single PE binary that comes out that you can then go and sign and validate. The original purpose of UKIs was to basically give, like, to create to propagate UEFI secure boot properties all the way into initmfs and command line. Make sense? Or did my
well,
audio just
I understand the concept. I just, none of this is implemented in a way that any of Hyper-V can load today. Now, that doesn't mean we couldn't do it, but the assumption that UKI already supports this and that's all well and good, but it doesn't run in an environment where Azure can go make decisions about what to load. So if UKI were to be usable, there would have to be a standard that we can consume.
Okay, how do you get back to square one? All of this is in guest. Azure or Hyper-V doesn't have to decide anything at all. All it does is
Sorry, I thought you were making the point that the UKI mechanism would be used to decide which of the various host-specific firmware bundles would get loaded in the second stage.
correct, but all of that is happening in the first stage inside the guest. You already have a guest running, and that guest goes and executes the UKI as a normal standard UEFI binary.
I don't understand how you can do that if executing into the target-specific guest reinitializes the confidential VM measurements. There is the management of the supervision of what content goes into a confidential VM is at the discretion of the VMM. It's not at the discretion of some other guest. It's a guest that is hosted by the VMM itself. So there has to be a path where you can go issue, like in S&P terminology, I can go issue S&P launch update and say, here's more data, here's more data, here's more data. And so, you know, at least as we have conceived it, that is a host operation. There is no operation where we can say, where some running stage one guest can say, I'm creating a second VM, please go push these pages into it through launch update.
Okay.
So I don't know if that's
Let's
your
walk,
proposal.
let's walk through the flow.
Okay.
You boot up a normal VM, a normal CVM, right? Everything just as today. It comes up with your UEFI. That UEFI goes and initializes all the tables properly, and it boots into a working PE binary, but maybe a UKI, right? That binary,
this is the first stage.
this is the first stage.
Where I think
we're starting from the beginning.
Sure.
So you're
where
running.
I think we would not want it to be a confidential VM because the fact that the customer has no control over it means that we have no reason to believe it's trustworthy. So running in a non-confidential VM should be just as good.
Yep, works for me.
Okay, great. Let's assume
I
it's
think,
a non-confidential
I think
stage one.
I think it doesn't make a big difference. It's
Okay.
a bit
Sure.
easier to reason about this, the type of VM if you make it consistent,
Maybe.
but whatever.
The reason I insist on non-confidential is that it reinforces the fact that we're not making assumptions that any confidential state persists between the first and second stages.
Yep,
So, okay.
Yep,
great.
absolutely. Works for me.
Great. Okay.
So you boot up that VM, right? Everything is good, it works. It then decides, I want to bootstrap myself into a confidential VM setup. So it issues hypervisor communication. The hypervisor communication today is using a VM firmware update thing, which is implemented using firmware config. I don't think you have any of those constructs. You would need to implement different constructs, which is Hyper-V specific then. That's okay. So you would need to enable those as part of that specific binary that loads, right? And you would need to implement the backend in your hypervisor that allows you to then basically upload an IGVM file into, or not upload the file. You would point the hypervisor to a memory location that contains the IGVM file. And the hypervisor then can go parse that file and reconstruct a completely new VM context based on that.
So all that makes sense to me. Especially when you said the content of that initial, well, no, I'm going to go back because it doesn't quite make sense. The content of that initial image is Hyper-V specific, and it uses Hyper-V specific logic to go decide how to load the second thing. That's all great if you are willing to rely on the fact that the customer has no control over what is in there. And it wasn't clear to me. I thought you were saying earlier, and the whole reason you were relying on UKI and so on was that you wanted the customer to provide the first stage. I think you're saying, no, the customer doesn't provide the first stage.
Correct. The customer only provides the customer provides the disk image for the first stage.
Why is that even necessary? If the first stage is so tightly coupled to a host, because, for example, that mechanism where you go tell the hypervisor, this is the set of things that I want you to load as the second stage, why would the customer have any interest in, or even why would cloud vendors want to take on the maintenance burden of distributing something that is stable across multiple generations of their host software that knows how to do all this type of loading?
The whole point of this exercise is to enable customers to reason about the full launch digest from source to digest.
Sure. I guess what I'm wondering is there a way to decorate, I'll use IGVM just because that's what we seem to be kind of moving towards as the stage 2 format. Why wouldn't we decorate IGVM with appropriate metadata that says if you're running on Hyper-V, this is the set of pages you need to load, and if you're running in GCP, this is the set of pages you need to load?
I don't see how IGVM plays any role, particularly in the execution phase.
The idea would be to eliminate the customer from the first stage altogether. The customer's intention of what they would like expressed in the second stage is expressed entirely in that second stage format, and then the host can run
what is the second stage
host-specific logic. The format that contains the customer-provided image.
Yeah. So how does the customer provided IGVM? Let's talk about IGVM. How does the IGVM go from customer intent into hypervisor? What is the path?
My first assumption is that we would extend the format to include sufficient information.
Ignore the format. Let's just assume it's a Hyper-V only IGVM. I don't care for now. how does that file go from the customer that builds the IGVM or vents the IGVM from someone who isn't Microsoft into their Azure Stage 1 VM or into whatever,
Well,
even to Stage 2? Like how would they even launch that?
Yeah, I don't know that it's interesting to look at it if this is only Azure, because if it was only Azure, we would just ingest the customer IGVM and boot it directly. There would not have to be a first stage because we would know what is the second stage we're running. It's not really, you think of it as an extended disk image. It's not any different than saying I have the customer's disk image. I have the customer's IGVM. That's just what I boot. I think the reason that that two stages are interesting is so that you can make a decision in the first stage about how to load the second stage.
Correct.
Which pieces of it are of interest?
Not only which pieces, but also have a standardized way of booting. So in the word that you were describing, right? You would basically, if you register an image into your cloud, you would need to register a disk image and an IGVM file, correct?
Yes.
Yes. And what I described earlier is that we moved away from that scheme a while ago for very good reasons, because it allows you to perform a bunch of pre-calculations, determining things ahead of time, updating things on the fly, and so on and so forth. It allows you to perform work before you even get into executing the target image. So you give customer code execution abilities before they even launch that IGVM file. That's the point. Plus, you only have a single artifact to worry about. It's only the disk image. You don't have to worry about two artifacts that need to then go and work in conjunction. You have a single artifact. Because the next thing that comes in is that IGVM file is not only built for Azure, it's built for Azure specifically with that only this one particular target disk image.
I'm sorry, I can't wrap my head around how this flow would work.
I think perhaps if we asked a couple of questions, we might help to clarify this. So, Alex, when you said that you eliminate effectively the IGVM part from the first boot, one of the utilities that Azure has is that we can actually we can reason about the hashes required for the IGVM piece and allow the customer to do all their updates on first boot. What is it you think is the good reason for forcing them to effectively do a two-stage boot process? I think that's the bit we're having the hardest time wrapping our heads around.
So what you really want to have is you want to have a firmware that only allows you to execute a single target binary you vet. So your firmware is tightly coupled to the disk image. It's not a generic firmware. It's a disk image specific firmware.
Right, but the IGVM file can provide that. That's why the standard format was invented.
Correct. And that's why we talked about the fact that we wanted to reuse IGVM as the transmission format from stage 1 to hypervisor, so it can then go and seed stage 2.
Right, but I think the question we're asking is, assuming the cloud already has the flexibility to boot customer-specific firmware, what is the additional advantage you see in doing this two-stage mechanism?
I see. The main advantage is you have a single artifact, right? It very quickly becomes messy if you have a multiple images that you need to maintain for a single target VM. If Azure has that sorted out, by all means, be my guest. Not everybody does, and it's not necessarily compatible with all the schemes we have out there. And this only, like to disentangle them usually only makes sense if you can cross combine them. So if your artifacts can be mixed and mashed in different ways. But here, because we're creating such a tight coupling, it's really just a single thing. And if it is a single thing, then by all means, it should just be part of the target disk image. And if it's part of the target disk image, you have two options. One is you can go and execute code in order to get it out of that image. That runs inside a guest context, or you can execute code to get it out of the disk image that runs outside of the guest context in the hypervisor. And if I have the choice, I much rather run something in a guest context than in the hypervisor context.
I can
I
speak to this a bit more in terms of like the complexity of distributing the firmware as a separate resource. You have to tell the service that you're not just going to start from a particular image, but you're starting from an image and a firmware resource, and you have to have registered that firmware resource with the service, and the service will need to ensure that that firmware is co-located with that disk image on the machine that is going to run the VM. So there's just a lot more coordination that needs to happen in order to get that resource to where it needs to go. It makes a whole lot more sense to have that firmware resource just in the disk image to start with. And if we're able to put this through something like the UFI forum for a protocol to provide the standard interface, then we can still have the cloud-specific firmwares and VMMs to implement the initial communication channel, so that we don't have to implement QEMU's firmware config interface, but we still provide the same semantics of loading an IGBM file. It will. Yeah.
Well, I was going to say, I really like the idea of pursuing this single artifact goal. I mean, that makes a lot of sense to me for, all the reasons you just said. There's a couple things I'm still hung up on, though, which is first, I really struggle with the idea of trying to provide a stable interface that allows stage 1 to run, because I can easily envision that in order for us to maintain maximum host flexibility and efficiency, we're going to need to change what stage 1 does in future versions of the host. Part of the benefit of having this two-stage model is, yes, what the customer finally runs is stable, but the way I get it loaded is something I have a huge amount of flexibility over. So to say that the customer has to provide the stage 1 image sounds very problematic to me. The other thing I'm hung up on is the idea it's all just a disk image and it's all just files in a file system. The disk image, at least in many of our models, is encrypted. And so until you are running inside the CVM, you can't get the keys that are used to decrypt that image. And so it's not clear to me how a first stage could run if it isn't customer provided, and it's not clear to me how we could support a stage 1 that is customer provided. So that's the stumbling block I'm hitting here.
Yeah, so you're not booting into the whole image that gets decrypted. You're booting into a UFI application that determines if it continues booting because it's on the right firmware, or if it needs to go and reset the firmware. And this would be on the EFI system partition, and that part is not
which is not encrypted.
Yeah.
So I mean, I guess what you're advocating is that there should be some EFI boot application that knows how to go pick apart the rest of the file system and say, I've got a standard way. Like, I think, rather, let me put it differently. What you're envisioning is that stage 1 is an EFI boot application, and that stage 1 has some reasonably standardized interface, standardized through UFI perhaps, to say, this is the rest of the stuff that I want to reset into when you go do the reboot.
Correct.
That all works, but it has what I see as significant performance downsides, because you have to go through all of the machinery to get the VM into a state that you can start the UEFI environment and go launch an application. And that's not all that cheap. If there is a way that you can provide instead a schema that helps you evaluate the second stage image, so the the VMM loader can make all the decisions that would have been made in stage 1, then you can skip the process of actually having to instantiate a full VM with a running UEFI and just go straight into the final customer image. And this is why I was advocating extending the IGVM format to embody that schema that allows stage 1 really to be a host-provided thing, which might not even be in the VM context, but just some host thing. And the schema is rich enough to allow the customer to describe exactly how they want their confidential contents to be manifested on that particular host.
Well, actually, I think we could go further and describe a cloud-specific problem where the scheme will actually detract from what we do, which is we do have a lot of services in the cloud that effectively run as workloads on our cloud. Boot times for those services when we have to upgrade them or restart them is very critical. If we have to follow a two-stage process, it's going to slow us down and we'll start missing SLAs.
Well, for first-party services, that's not a big deal because this two-stage mechanism is only needed for customers that desire the ability to provide their own boot chain end-to-end.
Right, but for 3P services.
Yeah, and there's a lot of those that I think can't suffer the performance problems that I just described.
Now let's go to another scenario that you haven't described, but I think which might be more valuable, which is you're thinking of this as the initial bring up stage, but there's also a VM maintenance phase where a customer effectively wants to do an RPM update of their entire image. And part of the problem there in the current cloud configuration is then they have to go into the cloud control plane and update the IGBM stuff to get it all to work if they want new firmware or new everything. What this mechanism would provide is basically a single stage way of doing what's effectively a cloud plus firmware plus configuration upgrade. That sounds quite valuable to me.
Yes, I completely agree with that.
Yep. To go back to the earlier point you made of how do we get this immediately into the first stage? I've been pondering on that one before we incepted this approach. The big issue I think is an ideological problem. In our hypervisor we don't have hardware access to customer resources, so we don't even have a driver that would allow us to go and access the disk, for example. All of that is responsibility of the guest of the virtual machine that only executes customer code at that point.
Do you
So-
have the ability to load CSP provided code into a customer VM if it is not confidential?
Yes.
So, I mean, in that case, imagine that you did what I had described, which is that you could put a schema into the IGVM file that describes how it is loaded. Essentially, UKI-ify the IGVM file. Now, it seems that what you could do is create an AWS-specific image that gets loaded into a customer VM, and what its job is to do is to pick apart that UKI IGVM to decide what to do and proceed with the load. So if you need to do everything within the guest context, that's fine. You can do it using AWS code inside the guest context to get to the point that you've gotten into stage 2. But
Okay,
you're
let
not
me-
requiring all the hypervisors to do the same thing.
Yeah, let me go and rephrase what you said in a more
Yeah,
technically
okay.
concrete way. Also, let me just clarify the statement I just made on the
Okay.
fact that we can inject random code. We can't inject random code. We always just run the normal firmware, right? But the firmware is provided by the hypervisor, and so the firmware could be enlightened to look for a different boot path, for example, that then could go and execute this particular IGVM file. So what you are saying is we could enlighten our OVMF binary that is part of the boot, the first stage boot, to go and find, say, a different file location on the ESP that contains the second stage IGVM, load that, and implement the loading part ourselves, correct?
Yes.
Okay.
It comes down to this goal of saying, I mean, the conflict here is you want as much as possible for the customer to own the logic that decides how to pick apart the UKI to figure out what to load. And I want as much as possible not to be required to create an environment where customer code can run in order to process that. You want to run it in a VM because your architecture requires that. I want to not run it in a VM because my architecture makes it difficult to do that. So what we really want is an abstraction that says different clouds can do it in different ways because the customer provided artifacts don't require any customer provided code to be involved to ensure that the second stage gets loaded correctly.
So in theory, like if we were to pursue the current or continue with the current UKI path, right? You would effectively need to go to you would open that disk image, try to find the ESP, do a mount of the ESP, find the boot file in there, find that it's a UKI, find that it does contain the IGVM section and pull the IGVM out of that. correct?
If it were possible for me to do all of that without having to be in a guest environment, so no UEFI interfaces, but I can do it all from outside of the guest, then I think we can make it work. We just have to, like I said, design the formats and interfaces such that you don't need guest code to be running to make the right decisions.
I see what you're getting
I
to.
mean, the interface ultimately talks to the hypervisor. So if there is other mechanism for the hypervisor to consume the IGVM file, then like we can implement that certainly. Just maybe
Yeah,
one is through the interface and the other is through whatever other means that is
well,
convenient to you
the point
guys.
that I want to stress, which I think Alex is understanding, is that that interface, if that interface is embodied as something that customer provided code can call, then there has to be an environment in which that customer provided code can run. And the only environment that you can use to run customer provided code is a VM. And having to stand one of those up to make the environment functional enough to run that customer code is the problem that I have. What sounds like a better approach to me, and I think, like I said, I think Alex is understanding this. I don't think neither he nor I knows exactly how to go pull it off, but if you can decorate the stage 2 in such a way that some host provided code can pick it apart and understand what the customer's intent was to do it, then you can make your own host specific choice about where that processing runs, which may or may not be inside of a VM, and to accomplish the right task. So the interface then, instead of becoming an application programming interface with like binary calls, the interface becomes a schema, a data schema that describes what the intention of the load is supposed to be. In a similar way to UKI holds a schema that says, this is how you decide which of the pieces of me you're supposed to load.
I have very little experience with handling virtual machine disk image formats, but it sounds like you're saying that we need to know how to parse just enough of the disk representation to determine if it's going to need to replace the firmware.
Well, I mean, Alex gave an example flow, which is you mount the customer disk and you find the boot partition and you look in there to see if there is an IGVM file. And if there is, you pick it apart to decide how to load it. So I think, yes, if you're not running inside of a VM, you would have to do exactly those things in the host. But, the host can make a choice whether it wants to do that or just start up a VM that mounts the disk and figures it out inside the guest. You at least have the choice in that case.
Yeah. And then you would still want to, for the other use case, right, of updating, you would still probably maybe want to have a way to actually explicitly invoke the interface, or would you just do a reboot and expect that you pick up the new IGVM file?
Yeah, my first instinct would be that while you're running inside the guest, you rewrite the IGVM file in the boot partition so that on the subsequent boot, you know that that's the one that we picked up.
I see. So one of the reasons why the Fuki thing is so compelling is exactly the same argument we had earlier with multiple artifacts at the next layer. So with that UKI concept, we can bundle a firmware that is only ever able to execute this one kernel and this initRD and this command line with the binary that bundles that kernel and the initRD and the command line. We can have a single artifact that also is as a single thing updatable and maintainable, which is a very compelling thing to have.
Yeah, I think there are ways to achieve Well, maybe it depends on what you mean by single artifact, but I think there are ways to achieve single artifact. Other ways to achieve single artifact. You're saying I want people to have a single artifact that says this firmware, this disk image, this kernel, this initRD.
I want to be able to say this is I have a Red Hat image, I boot that. And if it boots up, it only, like this image guarantees that I'm only running genuine Red Hat code inside. If I boot that image, then it can decide, am I running in a CVM context? Am I not running in a CVM context? If I'm not running in a CVM context, it can still get measured through a TPM. If you do trust that TPM, then in a CVM context, it can then go and decide, no, I need to have the IGVM. That's what I need. Now, I hear you on your
Sorry,
requirement.
I want to explore that idea just for a second, if that's okay. If you are relying on a UEFI boot protocol, I think it becomes a little bit challenging because UEFI is expressly designed to be able to load arbitrary images. And you can use, secure boot to make sure they're signed in a particular way, and you can use measured boot to come back later through your TPM and find out if it's what you expected. But in order to get the proof you want of I'm only running Red Hat code, you have to have UEFI measured boot. An alternative is to say, and this involves more kernel work, but an alternative is to say, I'm going to have an IGVM file that contains no UEFI, but just contains the kernel and the initRD. And now I know that because it's part of my initial measurement, I got the kernel and the initRD that I wanted.
You cannot boot that VM. Wait, no, I don't follow. Say again.
But the idea is to I've heard this discussed before. Eliminate UEFI from the boot chain and just go directly into the kernel. So the idea would be construct an IGVM file that just goes directly into the kernel, where the initRD is part of the initial.
This is called direct boot.
Yeah,
it's KVM direct boot.
I mean, that really gives you proof that you're only running the code you want, because that's the only thing that's in there.
We're getting to the top of the hour, and I would love to have this conversation continued so that we can make progress on a unified solution. Our folks on this call also on the Linux Cocoa mailing list and willing to move the conversation there, or do you want it to be in the QEMU Devel mailing list? I think Linux Cocoa is probably more appropriate.
Well, as someone who develops neither QEMU nor Linux, I'm not on either of those mailing lists. I feel like a great next step. Alex has heard a requirement that he hasn't heard before about trying to come up with a design that avoids the need to spin up a VM to run the stage one. I would love it if Alex could spend a little bit of time with all of the background and knowledge you have to see if there is a way to adapt the ideas that you already have to satisfy that requirement. Because if you can propose something that might just be like the last thing that gets us over the hump.
I can try.
Thank you.
All right, so to continue this thread, I guess we'll have everybody that's been in this call on the thread and CC Linux Cocoa for the transparency, if that works for people.
That works great for me if everybody else is willing to do that.
Yeah, let's do that.
Sounds good to me.
All right, thanks everybody for your time.
I appreciate you guys taking the time to walk me through this from the beginning. I found it very helpful, even if it was time consuming.
Me too. Thank you.
Thanks.
All right. Have a good day. Bye.
Bye, everybody.